All right, good afternoon, everybody. I feel like the class size gets progressively smaller every week, on average. Did I scare you guys away? I didn't scare you guys away clearly, but dang, I didn't think I would scare anybody else away. All right, we're talking about momentum and impulse. Just as a reminder of what those things are, momentum is defined. One object's momentum is its mass times its velocity. Momentum. If you are talking about more than one object's momentum, the plural, fun fact, is momenta. I don't know why, that's just the way it is. And then the other important thing that we learned, there's a couple things that we learned about. If we sum up all the external forces acting on an object, not the forces that count as interactions between objects, if those sum up to equal 0, then that means that the total momentum, I'm going to say tote, is conserved. Okay, meaning tote initial is the same as the total momentum at the end. Okay. The other thing to keep in mind is that when there are external forces, then we have a quantity called the impulse, and that is the sum over of the force accumulated over a period of time during which the external force is acting. So, for example, like we talked about, the cushion. Okay, a cushion would be an external force. Okay. T initial, T final, and usually that's a pretty small window of time. And then that also equals an object's change in momentum. Okay, they are the same thing. The way we can get, on average, the average force, because force is so important to us, the average force is basically 1 over delta t. It's basically just averaging the impulse over the time window. So it's the force times dt. Fear not, you will almost never, ever perform an integral in this class with impulse or momentum. But just as an idea. More often than not, what you'll just end up doing is you'll call the impulse just the products between force and time. But more often than not, that's what's going to take place. And that's basically everything that is in, short of actually talking about rocket propulsion. That's everything in chapter 9. That's it. Or that's everything that I care about. Okay, everything there. I believe in chapter 9 there was also some mention of center of mass, which I'm going to just throw that in there with rotational stuff. So we'll see center of mass later. Center of mass plays a little bit more of an important role, in my opinion, with rotations than it does with momentum. And having said that, today is basically just going to be a day where we are going to work through some examples. And that's basically all I have planned today. There is one housekeeping thing that I'll say while I'm up here. There's a 50-50 chance that we might not have class, we might not meet on Monday. And that's honestly probably not the worst thing ever, because Dr. Kerfoot was hanging out and just checking in on me to see how I was doing. And he was letting me know that I'm moving pretty fast, so that might not be the worst thing ever. The other half of that is we have our exam coming up, so I figured if we don't meet on Monday, then we can just do an exam review on Wednesday, and then all's well that ends well. Okay. So, I will let you guys know at the very least on Sunday night, so that you guys don't waste your time if you guys have to commute here or whatever. I'm hoping that everybody will know at least on Sunday night whether or not we're going to meet. So just stay tuned. Stay tuned on Canvas is all I got to say. And with that, I'm going to do a couple of examples first, just on my own, and I'll walk us through them. And then I have a few harder examples where I'm going to let you guys loose to work on them on your own. Okay. So the first one is a picture. Okay. I'm going to use purple. Actually, no, purple was awful. Purple made a huge mess. Okay. So here is my drawing of, this is the grass, okay, and then there's a T, okay, and then that is my golf ball, that is on it, it's slightly tilted, okay. There is a driver, a club. This is not going to be the best drawing in the world. Okay, that is my driver drawing. The golf ball is initially at rest. Okay, the golf club and the golf ball are in contact with each other for 6 milliseconds. That is not 6 meters per second, that is 6 milliseconds. Okay. And then it leaves the club face, okay, once the contact window is over. It leaves at a speed of 80 meters per second. Okay. The question that I have for you is I would love to know, this is important, the mass of the ball, the mass of the golf ball is 51 grams. 51 grams. Okay, so my question to you in this case is what is the average force that's delivered by the driver to the golf ball? Okay, that's my first example for us. Okay, let me put the ball in your court for a moment. Any ideas of where I could start with this? Bingo. Exactly. So I think that's a great place to start. So I know my change in momentum. That's my M. That's going to be my MV final minus my MV initial. And just in case we're worried about that, that's P final minus P initial. Okay. If I'm trying to find the average force, that's going to be that's just delta P over delta T. In this case, I know both of those things. What's my initial momentum of the golf ball in this case? If it starts at rest, it's going to be 0. Okay, so this is actually pretty straightforward. Okay. So that's whatever the mass of my golf ball is, times its final velocity, divided by the window of contact that the window of time that they are in contact with each other. And then to get this in terms of newtons, there's a couple things to keep in mind. This was specified in grams. That was in grams. And this was in milliseconds. So how do I get from grams to kilograms? How many grams are in a kilogram? 1,000. Sweet. So this is what did I say? So my answer would be 51 times 10 to the minus 3 kilograms times 80 meters per second. That's a close parenthesis. And then how do I get from seconds to milliseconds, or from milliseconds to seconds? Yeah, it'll divide by 1,000. Right. So this was 6 times 10 to the minus 3 seconds. Sweet. The answer I got when I plugged all of that into my calculator, I got an average force. Check me on this, but I got an average force of about 680 newtons. Something like that. That's not a small amount. And because I am completely oblivious to the conversion between newtons and pounds, just so we have some scope here. Newtons to pounds. So 680 newtons. That is momentarily the force of about 152 pounds. So it's not insignificant. Sweet. Not so bad, right? Not so bad. I can foresee either or both homework problems that have to do with baseballs. Does a baseball, when we're talking about a baseball being in contact with a bat, does the baseball start at rest, typically speaking? Unless you're playing t-ball, right? It's going to start at some speed. So a common mistake that I can see in the example of a baseball, this is my baseball, is that it's initially, I'll do it from this side, right? I'll do it from the first base side. So it's going to come in at a certain speed, and it's going to leave at a certain speed. Okay, just keep your signs straight, is all I gotta say. The signs matter. Okay. Sweet, any questions on that example? That's not even the worst thing ever, right? I feel like that's pretty Kool-Aid right there. Cool. All right. Example number 2. This is something that I am hoping that this is an example that I'm gonna put in your back pocket and then save it for Physics 4C. But I'm gonna erase this. Okay, we'll do an example. Okay. Anybody heard of the Large Hadron Collider? Some people shake their heads. Okay, basically, at the Large Hadron Collider, it is a like 26. I don't remember if it's kilometers or miles. I should know this. It is basically a giant circle, okay, underground, where over however many kilometers or miles it is, but I believe the radius is 26 kilometers. So you can just imagine how long a proton is going to be accelerated for. These protons are accelerated near the speed of light, and then they're smashed together in the idea that they can separate subatomic particles together. But those particles are accelerated very near the speed of light. In this example, we're not quite even close. We're 3 orders of magnitude off. But in this example, I have a proton. I'm going to call this a proton. That would be a proton. Proton. I'll just call that P plus. Okay. A proton is traveling, what did I say, at 5 times yes. Okay, a proton is traveling at some speed. Okay, so it's speed initial. I'm going to use a subscript of P for proton. Okay, it's traveling at some initial speed. And it collides with a helium atom. Okay, so a helium atom, to my knowledge, is 2 protons, 2 neutrons. So something like this. Something like that. And it is initially, I'm going to use He for helium. It's initially at rest. So this is initially. After impact, okay, impact, The proton moves at some speed. I'm going to just give us a hint and say that it goes back that way. V final proton. And then my helium nucleus, okay, is also, that's going to be my V final of my helium. Okay, I want to know two things. Given that the mass of a proton, mass of my proton is 1.66 times 10 to the, get this, minus 27 kilograms. Okay, if a proton hit you, do you think you would feel it? At that, nothing at this campus could measure that mass, I don't think. That doesn't say that much because it's really small. Okay. And then the mass of a helium atom, is 4 times the mass of a proton atom. I want to know two things. If the final velocity of my helium nucleus, is 5 times 10 to the 5th meters per second, I want to know what both my initial velocity and my final velocity are of my proton atom. So I want to know what V initial is, question mark, and I want to know what V final is, question mark. Okay, there's two assumptions I'm making. Okay, so my assumptions. Okay, this is an elastic collision. Okay, and remind me, what is a and what are the two quantities that are conserved in an elastic collision? What's up?
There's 2 objects in it, right?
Yeah. An elastic collision, what are my two quantities that are conserved?
Total momentum.
That's one of them. And kinetic energy. Okay, sweet. Cool. So, E tote and KE tote. Okay, that's going to be kind of my giveaway for how to set this up. And I'm assuming that everything's going to take place in one dimension. Okay. So if my assumptions are, I'm assuming that this is going to be true. And these acts literally just like two handballs that are just going to go in and out on a track. Because this is an elastic collision, I know two things. That my total momentum is going to be conserved. So the way I'm going to write that down, I have two things I'm dealing with. I'm dealing with my proton, and I'm dealing with my helium nucleus. I'm going to do it over here. And I'm going to do it in green. So my momentum is conserved. So elastic collision. Tells me immediately that total momentum, so total momentum initial equals total momentum final. Okay, and the same thing. My kinetic energy is conserved. So KE tote initial, that's the same thing as KE tote final. Sweet. Some things that'll make our lives easier. If my helium atom starts at rest, what's its momentum and kinetic energy? 0. Okay. So the only thing that I care about initially, in both of these cases, so I have M proton, V proton initial, plus the momentum of my helium nucleus initially, which is 0. So because the velocity is 0, that's great. And then I have mass of my proton, velocity final. But I was initially told that I have a final velocity for my my helium nucleus. So it'll be mass of helium times the velocity final of my helium. Sweet. Any questions on where that came from? Cool. Same thing for kinetic energy. Okay, kinetic energy is similar, but not identical. 1/2 mass of my proton initial, but it's v squared in this case. Okay, and then I have 1/2 mass of my proton, v proton final squared, plus 1/2 mass of my helium atom, velocity of my, oh, I just used H, okay. Keep it, final HB squared, okay. Those are the sum of, that's my total kinetic energy. And again, I have 0 kinetic energy to start with for my helium atom, since I'm told that it starts at rest. Sweet. All right, where do I go from here? Any ideas?
Start plugging it in.
What can I plug in?
You have your helium for
Sarah, say that again.
your helium. Mass of helium right
I really like that, actually. That's a great idea. So I'm told that the mass of my helium atom is 4 times as massive as the mass of my proton. So here's what I'm going to do in both cases. Okay, I'm going to substitute all of this. Okay, and that'll be 4 times the mass of my proton and 4 times the mass of my proton. Okay, I made a substitution. What do we notice that we have factors of on both sides of my equal signs now, on both lines? Anything cancel out? Can I get rid of anything? Yeah, the mass of my proton goes away now. Now the mass of my proton doesn't even matter, okay? I have a mass of my proton over here, and a mass of my proton over here, and a mass of my proton over here. And then in my second line, the 1/2s are basically always gonna go away, okay? So here's another way I'm gonna make, actually, I'll just keep writing. Okay, so here's what ends up happening. So the mass of my proton cancels in this case. So what I'm left with is V proton initial, that's equal to V proton final, plus 4 times the final velocity of my helium atom. And then I have the same thing, basically the same thing down here. The 1/2s all cancel, and the mass of my protons cancel. So I have V, my squared, my initial velocity squared, and then VP final squared, plus 4 times V final of my helium atom squared. Cool. Hey, that's not so bad, right? Now what? I have 2 things that I'm looking for, and I have 2 equations to do them. What do you guys think I need to do? Cry? Curl up in a corner? I feel that. Winter's over now, so that's my crying season. So I'm not gonna curl up in a corner anymore. Now what do I do? Let's remind myself of the 2 things that I'm looking for. I'm looking for my initial velocity of my proton and my final velocity of my proton. Did I find it yet? Nothing? Any ideas? Where to go from here?
the square root of both sides for the kinetic energy?
Sure. Sure, that works. So take the square root of that side, take the square root of this side. So I get, what did that do for me though?
So that you get an initial velocity for the proton set equal to the other equation.
I like that. Sweet. So I get, let's see here. I get, so I get VPI initial, and that equals square root of VP final squared plus 4 times V final for my helium atom squared. Okay, I already know what that is though. That's from my first line. Sweet, so I'm just gonna set those two things equal to each other. So I have square root of, I guess, square root of VP final squared plus 4 times V final for my helium atom squared. And that's the same thing as VP final plus 4 times V final for my helium atom. Okay, now what? Now I have one equation. What's the quantity that's unknown in this equation here now? Did anybody go to Roosevelt High School? Did anybody go to Roosevelt? You guys went to Roosevelt? Did you guys have Mrs. Parks as an English teacher? That's my older sister.
Oh, really?
Yeah, that's my older sister. My older sister and I, we are the kings and queens of making things awkward for you guys. You guys might know that. Yeah. Sweet. So, I know where to go. I want to know if you guys know where to go. Man, just imagine what my parents had to go through. There were 2 of us. What am I solving for?
Initial, right?
That's one thing I'm looking for. I'm also solving for my final velocity, aren't I?
It's putting it right there.
Yeah, so I'm looking for this, right? Sweet. I know my final velocity of my helium atom though, right? That was given to me. Sweet. Sweet. I know where to go from here. Now what do I do? What do I do to find this? Any ideas? From here?
Start plugging stuff in and solve for stuff.
Start plugging stuff in and solve for stuff. I like that. So if I plug in my numbers here, is that going to give me a solution yet?
So you have to put one side over to the other side so that you solve for it.
I like that.
Divide that.
I like that. Sweet. So I'm trying to solve for my final velocity squared. Okay. Here's what I'm going to do. I'm going to square both sides. Okay. So the square root just goes away over here. I get V proton squared plus 4 V final helium squared. And then I have to go through all the blah, 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 the factoring things out and all that stuff. Sweet. So good news is this is something I've done a million times. So VP final squared. It's those two things squared, so plus, that would be 16 V final helium squared. And then it's twice the product of those two things, so it would be plus 8 V proton final V final helium. Okay, sweet. Okay, this is actually pretty nice. Here's why. There's a proton final squared, V proton final squared on both sides. Those cancel out. And then I have 4, and then I have 16 of my V final of my helium squared. So I'm gonna, I don't know, what do I want to do? I'm gonna cross that out and reduce that to 12. So now I'm left with, everything over here is gone. So I get 12 V final helium squared plus 8 times V final helium. Okay, I'm almost done. Now what?
Background, is it squared?
Exactly. So I'm gonna, one of those goes away, and one of those goes away. What I end up getting for my V final, for my proton, is minus, so let's see, I'm gonna subtract that over to the other side, and then divide by 8. There's a common factor of 4, so I get, what is that, 3/2? Minus 3/2. And that actually checked out pretty nicely. Sweet. And what does that minus sign tell me? Does it keep going in the same direction it was initially traveling, or does it flip around? Yeah, it bounced back. Sweet. So that kind of checks out with, that checks out, but only because I drew the picture though. So that's kind of nice. Okay. And then because we all crave to see numbers, what did I end up getting when I put it in my calculator? I got 7.5. So this is minus 7.5 times 10 to the 5th meters per second. So that's 750,000 meters per second. I can't even count that high. Okay, sweet. So I have one thing. That's great. Now what do I do to find, I still am looking for my initial velocity. How do I do that?
Found our final, right?
We found our final. I love that. That's great. Sweet. I'm going to take this value, and just, my easiest way of doing that is just plugging it right back in there. So what did I end up getting? I get, for my V final, to finish things off, that would be minus 7.5 times 10 to the 5th meters per second, plus 4 times, what was my final velocity? 5. Yeah, 5 times 10 raised to the 5th meters per second. Okay, so they have the same order of magnitude. This is just me thinking out loud of how to do this in my head. So that would be 20 times 10 to the 5th minus 7.5. So what would that be? 12.5, right? That's 12.5?
Yeah.
Okay, sweet. So that'd be 12.5 times 10 to the 5th. Here's how I would write that. So okay, keeping one thing in place here, and then my V initial of my proton would be, you could write it, we'll do it this way, 12.5 times 10 to the 5th meters per second. Okay, sweet. So concept check here, okay? If anything collides with something more massive than it, okay, I'm expecting, and it's a better question, and it makes it move, okay? So if I have, like my two, this is a really terrible example, but if I have my one marker and it collides, that was a terrible example. I quit, okay? So if I have something that collides with 4 times as massive at it and it hits it head on, okay, did this gain or did it lose kinetic energy post collision? What do we think? So did the proton gain or did it lose kinetic energy? Right, I would hope that it loses energy, right? Because at the end of the day, my proton hit this and caused it to move, right? When you cause something to move, would you agree with me if I said that we exert a force on it? Sweet, and force is basically just a way of sending kinetic energy from one object to another, right? Sweet. So I would hope that that object post-collision is going to lose kinetic energy. So this went from whatever. It went from that velocity to, what was my final velocity? Yeah, so it lost energy. Okay, sweet. The minus sign just tells me that it's going the opposite direction. Sweet, so that checks out to me. Sweet, and then because it started stationary and then it started moving, I would hope that my helium atom gained kinetic energy, which it did. That was all specified in the problem. Cool. All right, that's not so bad. Any questions on that one? Cool. Cool. The name of the game, as soon as you see an elastic collision, okay, especially one that's in one dimension, the name of the game is immediately write this stuff down. And you're almost always going to need to do some kind of substitution. Okay? Almost always. Sweet. And if Newton's laws wasn't enough, there it is again. Moving things around. Okay, sweet. One more time, any questions? Cool. Okay, moving on. Okay, I'm gonna do one more example, and then I'm gonna let you guys loose on. Yeah, I'll let you guys loose on one more after that. So hang tight. Okay, so I have a fun history thing to share. How do we measure today? How do we measure how fast like a bullet is traveling? How would we do that now? Any ideas? What's up? Someone said something. Like, I don't know, we have a whole host of technology available to us. Any ideas on how today, not just in Physics 4A, how we would go about measuring how fast a bullet travels? Yeah, I think light is a really good way to do that. Okay, light has the same speed in every reference frame, okay, in a vacuum, okay? So using, like, I don't know, photodetectors or something, we have sophisticated enough technology to get really accurate measurements. Okay, did lasers always exist? No, right? Human beings did not invent lasers until, like, I don't know, 100 years ago. Okay, which actually that's probably not even true. Probably closer to like 70 years ago at this point. In any event, right? That's like 70 years of having lasers, though. That's like not a whole lot of time. So if we wanted to measure how fast a bullet was traveling, or for the cases of like, I don't know, the Revolutionary War cannonballs, this is my really crappy drawing of how that was measured. We had a bullet, okay, that was something like this. Okay, and in this example that I'm going to do, we have a bullet that has a mass of, what was it? 15 grams. Okay, that's pretty small, 15 grams. Okay. And then what would end up happening is that there would be a pendulum. This is my drawing of a pendulum with a wooden block. Okay, and the wooden block has a mass of, okay, the wooden block is 3 kilograms. Okay, 3 kilograms. Okay, this is, I'm not making this up. This is how velocities used to be measured. This is called a ballistic pendulum. Okay, it's because you would shoot your ballistic object directly into it. Okay, sometimes for bullets it would be a wooden block, but like for cannonballs, are you gonna shoot a cannonball at a block of wood? Probably not, right? So what would end up happening is that they had these giant cauldrons, I'm not making this up, and they would blast them in there, and they would see how high up they went, and then they would use that to figure out how fast the bullet was moving. And we're going to do the exact same thing. So a bullet is shot into this wooden block, and post-collision, let's see here. I'm going to say that that's where it started. Okay. The block and the bullet stick together. So if they stick together, what kind of collision does that immediately tell you this is? It's an inelastic collision. Okay, sweet. So the bullet gets lodged in here. This is my really bad drawing of the bullet. Okay, it gets lodged in there, and I'm going to say that the the block reaches a height of, what did I say? 10 centimeters. A maximum height of 10 centimeters from where it started. Okay, and you go backwards, and we want to try to figure out what was the bullet's velocity when it made contact. And ideally, you're trying to say that for bullets that are moving that fast, or cannonballs, air resistance probably isn't going to make a huge difference. Those things are massive and super fast. So generally speaking, you're going to shoot it pretty close by, so you want to try to figure out the speed that it was shot at. Okay, this combines two things now. Okay, we have two things. Okay, so we agreed that this is an inelastic collision, right? Because they stick together. Okay, sweet. Initially, is my block moving? No, it's not. Okay, initially my block is just hanging there. Okay. So immediately what that tells me is momentum is still conserved, but what's not conserved anymore? Right, between the block and the bullet, the kinetic energy is not conserved. Okay, so the only thing that I have to deal with is, I'm going to say momentum's conserved, so P tote initial is the same thing as P tote final. Okay, so that would be the mass of my, I have to be specific here. So I'm going to say B for bullet times V initial for my bullet. Okay, but after they stick together, it's going to be M bullet plus, I'm going to say M W for wood, okay, times V, I'm just going to call that V final because they move together, okay? And just so we have a picture in our head, it's going to be traveling up here, it's going to reach a maximum height, and then it's going to come back down. Okay, sweet. Not so long ago, we also dealt with energy conservation, okay? If I have an initial velocity, I can figure out my maximum height that this goes, okay? That still works here, okay? At the maximum height, when any object reaches its maximum height when it's moving and it's launched at an initial speed, what is its final velocity when it reaches its maximum height? Sweet. So met. So my other half of this is I'm going to say that my kinetic energy, I'm going to say kinetic energy initial. This is kind of tricky, okay, because right here I'm saying initial is pre-collision and final is once they smash together. In this example, I'm going to say that the initial kinetic energy is the kinetic energy when the bullet is in and it starts moving, and then that is equal to the final total mechanical energy, but that's just the potential energy, so that would just be PE final in that case. Okay, so I know that the initials and finals are a little bit tricky to solve for, but keep that in mind. Okay. So let's see here. My initial kinetic energy in this case is going to be 1/2. What's the mass of my block bullet system in this case? Yeah, it's just put them together, right? So it's 1/2 M. I'm going to say block plus M W. Okay, and then my velocity, that's my whatever I find over here, my final velocity. V squared. Okay. And then my final height, I know that, that's going to be m, my mass of my object, so m block plus mw times g times h. That's my final height. Okay. Cool. And just like everything that involves gravity, the masses really, really don't seem to matter all that much. And that really bothers me. Turns out it bothered Einstein too. But hey, okay, so here's the thing that drives me nuts though, I'm initially just looking for this, right? I just want to know what my initial speed of my bullet is. I have two unknowns now. I introduced two things, okay? So I'm gonna work my way backwards because I know what this is, okay? G on the planet Earth, as far as I'm concerned, that as long as I'm standing near the surface of the Earth, that's not gonna change. So my V final squared, okay? That's the speed that my block bullets combination is initially traveling that way. I'm gonna take away that. That is 2 GH square rooted. Okay, those are all things that I know. I know my height. I know my final height. I know G, and I know the number 2. Okay, I'm working my way backwards. Okay, so I have MB plus M with a subscript of W times the square root of 2GH. Okay. And I'm almost done now, because now I have everything I need. I know what H is, I know what the masses of my objects are, and I know what G and the number 2 are. That's pretty great. Okay, so all I need to finish this whole thing off is just divide both sides by the mass of my bullet. Okay, and then I'm done. What did I get for my final answer? Of course I didn't write down the answer. All right, so let's see what we get over here. So I get 3 plus 15 times 2 minus 3. Nope, that's not right. Okay. Times the, nope, times the square root of 2 times 9.1 times 10 raised to the minus 2. Okay, and then that's divided by 15 times 10 raised to the minus 3. I'm imagining that this is going to be a reasonably big number here. 280 meters per second. That is ridiculous. Someone check me on that, though. I might be wrong.
What is MW stand for?
That is the mass of the wooden block.
Oh.
So that'll be 3 kilograms. Yeah. But 280 meters per second? Yikes. That's crazy. That's really fast. If you want some relatable units, do that conversion and see how fast that's going in miles per hour. That's still really fast. Doesn't matter how you slice that up. Cool. Okay. I'm trying to think. Are there any questions on this example here? Cool deal. Okay, the last one that I've got for you guys today, I'm not going to deal with that other one. The last one I'm going to deal with, I'm going to turn you guys loose on this one, okay? I'm going to draw the picture, and I'll give you guys 10 minutes to work on it. I'll check in after 10 minutes. Okay. Let's see here. My last thing is I have, remember how when I introduced this, I said that when you think of collisions, what's the first thing you think of? We all said car accident. Okay. This is where we're going to at least do some detective work to try to figure out what goes on with car crashes when cars stick together. So here's my picture. Okay, a car. This is going to be a top-down view. So a car. This is my car. That has a mass of 1,200 kilograms. Okay, is traveling due east. Okay, where its initial velocity. I'm going to use a subscript of c for car. I said 30 meters per second. Okay, and much to everyone's dismay, it collides with a truck, a semi-truck that is 3 times as massive. So I'm going to say truck, and I'm going to say M car. That is 3,600 kilograms. And it is traveling. I guess I shouldn't have said that. Okay. The initial velocity that's traveling at, it's at a weird intersection. Okay, its initial velocity is 20 meters per second, but it is, so that's going east, by the way. It's traveling 20 meters per second, but it is traveling 60 degrees northeast. So this is traveling 60 degrees northeast. Okay. Okay, they collide and they stick together, and then they travel some distance. I don't care how far it is, but I want to know what their combined speed is, and I want to know the angle that it is traveling at. Okay, so at the end of the day, these two collide. Truck plus car combine. In my optimistic brain, I tried to think of like a way to positively spin this around, and the best thing I could do was that they were transformers, and they were lost parts, and they had to find each other. I don't know. That was the best I could do. Okay, they combine, and I want to know what the final velocity is, which means I want to know what the final velocity magnitude is, and I want to know what the angle is. Okay, actually, you know what? I'm going to give us 15 minutes to do that. Okay, I will give you guys 15 minutes to check this out. I'll check back in 10 minutes. Sweet. So try this out. Now we're dealing with vectors. Okay, momentum is a vector. So now you have to break things up into components. Okay, that's my hint. Okay, 3, 2, 1, make it go.
asking the mass.
Right.
Mass.
Yeah.
Yeah.
We found out your velocity, your axis velocity, but then
Yeah.
velocity.
Wait, this is the trap. This is yeah, this is just traveling one direction. Yeah. This travel one direction. This has that. So you figured out right there is sine cosine, and we found that here once you just plug it back in, and then add this. The x component here is 17,000, and then divide it with 15 for x or something. So that y, and magnitude, and there.
Yeah, I don't know about that.
Square root, remember? Square root both these, and then square root for square root. Remember? Magnitude.
I was trying to see if I know. Oh, yeah, I do.
Okay.
Oh, yeah, just like that on my mind.
Yeah, and then now you find it inverse theta. Find theta. The angle. Yeah, yeah. So these, so like, we got this, right? So ignore the y now. When you have this now, it's traveling in the direction of x, and then have to add, multiply these things, and add that, that's the same. Yeah, yeah. So 300 is this, the mass is together, like 1200 plus 36. We'll use that one. Yeah. And then we get that, and then you find that, and then you go. Yeah,
That's what I
so
was
they
thinking.
can- Remember why and rise and run.
Yeah.
15.
Yeah, exactly.
It's close. Why is over run? Why is over the top?
Oh.
That's it. That's your enforcement. Yeah. Northeast. Is good stances.
All right, folks, let's finish this up. Let's see, what color did I use? Okay, I'm gonna use pink. I haven't used pink yet. All right. Okay, so here in my head, this is how I think about this. You can do this a completely different way. As soon as I see that I'm asking for a magnitude and a direction, okay, this is the first thing that might traumatize us. This is the first thing I'm thinking of, is that the magnitude of my final I guess that's what I should have written there. All right, the magnitude of my final velocity, that's Vx final squared plus Vy final squared, right? So I instantly have two unknowns, okay? But I think you'll see in just a second that I have two equations, okay? And it's the inverse tangent of my Vy final over my V final, okay? So that's the first thing that I think about, okay? So now I know that I need two equations that'll help me out, okay? And because momentum is a vector quantity, that means I have momentums conserved in both the x direction and in the y direction. Okay, sweet, I got those right. Okay, so, all right, initially, here's the deal. So in the x direction, let's see, in the x direction I have my car, in this case, my car is only traveling in the x direction. So should it have any momentum in the y direction initially? No, right, okay, sweet. So I'm gonna say mass of my car plus times its initial velocity of my car, plus the mass of my truck times the initial velocity of the truck in the x direction. Okay, and then they combine. Unfortunately, they combine together, and it becomes mass of my car plus the mass of my truck times the v final in the x direction. Okay? Sweet. I'm gonna leave a little space down there. I'm gonna do the same thing for the y direction. Okay? We agreed though that my car doesn't have any momentum in the y direction though, right? It's just traveling east. Sweet, so I don't even have to worry about that. So it's just gonna be the mass of my truck times its velocity component, truck, in the y direction. Yeah. And then that equals, same deal, mc plus mt, the mass of my truck, and then its final velocity in the y direction. Their combined final velocity in the y direction. Okay, now believe it or not, you're not that far away from being done now, okay? How do I find the x component of my truck's initial velocity?
So you have 60, and then you put 20 cosine 60.
I like that. Sweet. So this would be, I'm gonna write this out, plus mass of my truck. I'm gonna write v initial truck, since it's the x component and it's measured relative to the east-west axis, I'm gonna say cosine of theta, okay, and that equals mc plus mt, final velocity in the x direction. Sweet. So what does that mean I'm gonna use for the y direction? You guys are pros. I love it. Sweet. So it'll be mt v initial truck times sine of theta, and that equals, again, sum of my masses, and that's the final velocity component in the y direction. Okay. Hey, you're almost done. Okay. This is the part where I'm gonna blow through this because we're running low on time. All I need to do is solve for this and solve for this. So what do I get for my final expressions? So my x component, v final in the x direction, that's, oh my gosh, mc vic mt cosine theta divided by the sum of their masses, mc plus mt. Okay, my v final in the y direction is just m mass of my truck times its initial velocity times sine of theta divided by the sum of the masses. Okay, and then I have everything I need to figure out my final velocity, their combined velocity, and I have everything I need to find the angle. I did plug this into my calculator before I got here, and I got something along the lines of my final velocity magnitude was 19.8 meters per second, and then my angle was 40.9, yeah, 40.9. So my angle was 40.9 degrees, so that would still be northeast. Sweet. Sweet. That's sweet. The hardest part about two-dimensional stuff is just breaking it up into components. Okay, it is entirely possible that you could get an elastic collision that's in 2 dimensions. So in which case you would have a third equation that you could work with too. If we're gonna do that, we're gonna do it on Monday or Wednesday of next week. Okay. Any questions on any of the examples we did today? Yeah.
So with like the car collision example,
Mm-hmm.
you
would have like crumple zones and stuff, right, which would change it dramatically.
Say that one more time.
So like cars have crumple zones in the front, so that it
Hmm.
slows down over a period of time when it collides. So would that change the way we do the math?
That's a solid point. Realistically, the answer is probably yes. But I would say that would only, like in my professional opinion, that would probably only make a really small difference. The way that I can see that making the most difference is not necessarily in terms of doing the calculation that we do, but that might add a spinning component, which is basically the subject of what we're going to cover after next week. So all the spinning stuff. So that would be my best guess. But I don't know off the top of my head. Yeah, that's a good question though. Any other questions? Sweet. Okay, stay tuned to your Canvas page. I'll let you guys know what's going on Monday, and no matter what, I'll see you next week for an exam review either way. So have a good weekend, folks, and I will see you next week.